Okay, so welcome to this next video in the playlist on functional analysis. In this playlist we're going to introduce the concept of a topological space, and we're going to show how all metric spaces are topological spaces, and that's what we're going to show basically. So firstly, let's start off with the definition of a topological space and then show how metric spaces if you have a metric space, you can very easily use it to build a topological space, is what I want to say. Okay, so a topological space then. A topological space. And we're not really going to use the concept of topological space much in functional analysis. Metric spaces are abstract enough for us to be working with. But it's not, for completion, I want to include this little bit of a discussion. Okay, so a topological space, you start off with a set. So X is equal to a set. So it could be equal to a set of elements like capital V, lowercase v, and big F. And then what you do is, instead of defining, for instance, when we were defining a metric space, we then defined this distance function d. Instead what you defined is you define a subset of the power set of X. So you define a set which is called the set of open sets. So U is going to be a set containing a bunch of subsets, of the set X, of X. And this is called the topology. This set containing this bunch of subsets is called the topology. Okay, and we're going to define the sets that are in U to be the open sets. So sets which are in U are defined to be the open sets. Sets which are in U are defined to be open sets. Be open sets. Okay, so U is a subset of the power set of X. Now the power set of X is the set of all subsets of the set X. So if I do it for this specific example, then we have the empty set, and inconveniently I've used the letter phi here, so we'll have some other symbol there. So these are just symbols. So firstly we have the empty set, which is the set containing nothing. That's certainly a subset of this. Then we have all the singletons. So we have a set containing just a set containing the lowercase v, a set containing capital F. Then we have all the doubles. So we have the set containing a and v, the set containing a and capital F, and we have the set containing, what's to the left, phi and f, and then finally we have the set containing every single element, so a, phi and f, so the whole set itself. So that is all possible subsets of this set X, and they are all put in a set together, and that is called the power set of X. So basically a topology U is going to be, you pick out a bunch of these. So you might pick out this one, you might pick out this one, or you might pick out this one and this one. So you're going to take out some subset of them and put them into a set by themselves. So U is going to be a subset of the power set of X. So we could say the set containing the empty set, the set containing A, and the set containing AF. And we might say we want that to be our topology. And there's a problem basically, that this might not satisfy the axioms of a topology, because you cannot just define your empty sets willy-nilly like this. Your open sets. You can't just define your open sets willy-nilly. You have to pick them such that it then obeys some axioms, and these are the axioms that it has to obey. First axiom of a topology is that the empty set and the whole set have to be elements of this set. So in this case, this is satisfied because here is the whole set and here is the empty set. So first axiom of the topology is met by this set here. The second axiom of a topology is that if you have some ENs, which are elements of your topology. So if you pick out some sets here, and we call them, and we will label them E1, E2, E3. So E1, E2, E3. etc., all the way up to En, and n is some finite number, so you pick out finitely many of these, and then you intersect them all together. So the intersection n is equal to 1, and not to infinity, sorry, I is equal to 1, we'll say, to n. I should have labelled those ei, and it goes all the way up to En. Of ei's, that, when you intersect them all together like that, it has to also make you another set which is in your topology. Is this met in this case? If I pick any combination of these and I intersect them, am I going to always get another set in here? And in this case, it actually does amazingly satisfy that. So if you pick any finite combination of these, you're always going to, and you intersect them, you're always going to get another one of them. And the reason that is because this one is contained within this one is contained within this one, and this one is contained within this one. So basically, when you take any finite number of them and you intersect them, it's just going to be the lowest one basically that you pick. So if I took A and I wanted, so I took E1 to be A, I took E2 to be AF, and I then took E3 to be equal to A phi F. Then when I intersect these, it's just going to be the smallest one of these, because they are all contained in one another like that, and there's this beautiful ordering on this set. I know instantly that the intersection is going to be in here, because it's just going to be equal to the lowest one, in this case A. If you intersect all of those together, it's just the only element that's in all of them is going to be the set containing A, which is an element back in your topology. So this collection of subsets of our original set X, it does obey axiom 2 of topology. Now the third axiom is that if you take E alpha, which are elements of your topology, and now it doesn't necessarily need to be finite, you can have countably infinite many of these, you can even have uncountably infinitely many of them. If you take the union over alpha of all of these sets, union countably many, uncountably infinitely many open sets together, it still has to be an open set. So, if I union any of these two together, again, because of the way I've picked this, because of the incredible ordering of this, the fact that this one is a subset of this one is a subset of this one is a subset of this one, when I union any of these together, it's just going to be the one that's highest up. So if I union all three of these together, it's just going to be the highest one, which is this here. So in this case, again, it's going to satisfy that that axiom. So this is, in fact, a topology. It's not a very interesting one, because the real essence of what this is trying to capture, you can't really get just from a finite set. If you the definitions work perfectly fine in the case of a finite original set X, but it's fair to say that finite sets do not really capture what this definition was designed to capture. Okay, so in a topology, what you do is you have a set X and a collection of subsets of that set X called this big curly U, which is called the topology of this space. And together they form a topological space. And you can define a lot of concepts of analysis. You can define the concept of a limit just with this, a topological space. Okay, so and this topology here, which can also be often given the symbol tau, it has to satisfy these three axioms. Firstly, that the empty set and the whole space are elements of this set, that the finite intersections of elements of this set gives another element of this set, and arbitrary unions of elements of this set also gives an element of this set. So what we want to now see is that if we take a metric space XD and we define the topology to be equal to the set of open sets in the metric space, set of open sets in a metric space. So remember, we defined open sets in a metric space to be the sets which contain all their interior points. So we want to show that if you define the topology to be equal to that set of all open sets, where we're viewing open sets as being defined according to this metrical property, that indeed obeys all these axioms of topology, and that defines a valid topology on the set X. So basically what I want to show you is that from any metrics, if you've got a set with a metric defined on it, you can instantly construct a topology very easily by just saying that the topology is the set of all open sets, where we're defining open sets according to the definition that every point in the set is an interior point. Okay, so what I want to now prove to you is that that is true, that that this set of all open sets obeys the three axioms of topology, of a topology. That's all I need to show. So if I take a metric space, xd, and I define this, the topology, this set of subsets of the set X, so it's a subset of the power set of X, so subset of the power set of X, and I'm going to define it to be equal to the set of all, let's say, U, so U is often used to denote an open set, U, which is a subset of the set X such that U is open, i.e. U contains only interior points, so all points of this, all elements of this set are interior points, contains only interior points, i.e. U is open. Okay, so basically what I want to show is that open in a metric space corresponds perfectly with open, with the notion of open in a topological space. Okay, so first axiom I need to show is that the empty set and the whole space are elements of this topology U. Okay, well, we have discussed in previous videos that the empty set is open in the sense of metrics, because does it contain only interior points? Well, it contains no points, so it's certainly not true to say that it is not open, because if it were not open, then it would imply that there exists a point in that set which was not an interior point, and there are no points in here which are not interior points, so in a way it's vacuously true that this is open. So therefore the empty set would be an element of this set big U. Okay, similarly the whole space is most definitely open, because if you take any point in there, any point is going to be an interior point, the reason being that you can always, if you have your whole space here, if you take an element X in here, then take a ball of whatever radius you want. Take an open ball around X of whatever radius you want, where R is greater than 0, and this is assured to be a subset of X, because the only points in here are going to be points that are in X, therefore it's assuredly a subset of X. Okay, so X is open, so X is most definitely an element of this set, because this is the set containing all open sets. Okay, excellent. So second axiom of topology, that if I take EIs, if I take elements of this set, so if EIs are elements of this set up here, big U, then I need to prove that the intersection of them, the finite intersection of open sets, is also open. So I need to show that this intersection is going to be an element of U. So that corresponds to showing that if I take a finite number of open sets, that their intersection is also going to be open. Okay, so if you take so let X be an element. So if I want to show that this is going to be open, then I need to show that any point that's in it is an interior point. So let X be an element of this intersection, I is equal to 1 to n EI. That implies that X is an element of all of the little EIs, because if it's in the intersection, if I write this out as E1 intersect E2 all the way up, intersect all the way up to En, then if it's in the intersection of all of these, it means that it must be in each and every one. So for all I is equal to 1, 2, all the way through to n, X must be an element of EI. Now, EI is an element of your big set U, which implies that EI is open. So if EI is open, that implies that X is interior in EI for all I is equal to 1, 2, 3, etc. all the way up to n. Now this implies that there exists an epsilon greater than 0 greater than 0, and I'll say ER, epsilon, which is dependent on I, because it's going to depend on which set you are in. An epsilon I greater than 0, such that the ball, the open ball, at centre the x of radius epsilon I is completely contained within EI. So for all I is equal to 1, 2, 3, 4, so if I have the set E1, basically I can find you a open ball around the point x of radius epsilon 1, which is completely contained in there. That's just the definition of saying that E1 is open. And we're saying that it was open because it was one of these sets in this big set U, which was the set of all open sets. So if it's open and it's true that it contains x, then it must be true that there is a ball of radius epsilon 1, of some radius epsilon, which we're calling epsilon 1, which is contained within E1. And this is true for all the I. So for E2, there must also be a ball, an open ball centre the x of radius, let's say epsilon 2, which is contained within E2. And we can go all the way on to En must contain a ball, an open ball, around the point x of radius, let's say epsilon n. Now basically what I want to do is I want to define epsilon to be equal to the minimum of the set epsilon 1, epsilon 2, all the way up to epsilon n. So I want you to take the minimum of all of these balls here, and I want you to take the minimum of all of the radii of these balls and call that epsilon. Then it is true that the ball of around x of size epsilon is completely contained within the ball, contained within the ball of size x of epsilon 1, of epsilon I, in fact, but we'll say it gently. Epsilon is smaller, it is the minimum of all of these. So at the epsilon is either equal to epsilon 1 or it's smaller than epsilon 1, because if it's equal to epsilon 1, it meant that the minimum of all of these was equal to epsilon 1. If it's not equal to epsilon 1, it implies that there was some element in here which was smaller than epsilon 1, and that's the value of epsilon. So the ball of size epsilon is less than or equal to, is contained within the ball of size, ball around x of size epsilon 1, and that's true for all I. So the ball around x of size epsilon is contained within the ball of size x around epsilon I. So if we draw a picture of this, basically, let's draw a picture, that always helps. What we have is we have a bunch of sets, so I'm just going to draw 3 of them so it's clearer. We have a bunch of sets like that, and we are taking their intersection. So their intersection is this bit at the centre. Then what we said is there is some point x in there, so let's take x in there. There are 2 possibilities actually which I missed. Either the intersection is equal to the empty set, so I should have put that. Either the intersection is equal to the empty set, so I is equal to 1 to n ei could have been the empty set, is equal to the empty set, then automatically the empty set is an open set, so the intersection would have been an open set. Or if it's not the empty set, then I can find an x within the intersection. Okay, so you find this x within the intersection. Now what we're saying is if we look at each of these individual sets, so this is E1, E2, E3, they're all open sets and they all contain x. So around each of them, if we draw this picture bigger, here is x. For each of them, if we look at E2 down here, or is that E3? Yes, this is E3, so this is E3 here. If we look at E3, here's the point x. Now E3 is an open set, so there must have been a ball around there, an open ball around x of size epsilon 3. Similarly, for E1, if we draw E1 separated over here now, E1 again, here's the point x, and there must have been a point, there must have been a ball of some radius epsilon 1 around that point, which is completely contained in E1. And similarly, for E2, again, there must have been a ball of some radius epsilon 2 around that point, a point x. Now basically what I'm saying is take whichever one of these balls has the smallest radius, it's going to be contained within all the others, and it's certainly therefore contained within all of these sets. So take the minimum ball, and and that's going to be contained within absolutely all of them. So it's going to be contained within all of their intersection, within the intersection of all of them, and that's our proof that this is going to that's our proof that this intersection is going to be an open set, because I found you an open ball around any arbitrary point x which is still contained within the intersection. Okay, so the ball centre of x of size epsilon is completely contained within the ball centre of x of size epsilon I, where I varies from 1, 2, 3, all the way up to n, which implies that since the ball centre of x of epsilon I was contained within EI, it implies that the ball centre of x of radius epsilon is contained within EI for all I is an element of 1, 2, all the way up to n. Now that implies that the open ball centred at the point x of radius epsilon is contained within the intersection of all of these sets. Since it's in all of them, it must be in their intersection. And then what we've done is we have found an open ball. We have found an open ball around which is around an arbitrary point x, x, which is an element of this intersection, such that this ball around the point x of radius epsilon is completely contained within this intersection. I is equal to 1 to n ei. Okay, so that shows that property, that that it is true that under finite intersection, this set of open sets is closed under finite intersection, which shows that it does obey axiom 2 of a topology. Okay, so now axiom 3 then. Axiom 3 says that if I take arbitrarily many open sets, so all of these are elements of this set U, which is defined to be the set of open sets according to the metrical definition, and we take this union, this arbitrary union of them, and it could be finitely many, it could be countably many, and it could be uncountably many. It doesn't matter. Then that also needs to be an element of U. So we need to prove this. Okay, so we need to prove that this is an open set. So either there is a possibility that this is the empty set, that this union is the empty set. That's the case where absolutely every single E alpha is equal to the empty set, i.e. you're just unioning up the empty set. In that case, the union is most definitely an empty set. The other case is that this is not the empty set, therefore I can find some element of the original set big X, which is within this union of these open sets. Okay, so let little x be an element of this set, and what I want to do is prove that it is an interior point. Well, if x is an element of this union, then there must exist some set, let's say E alpha 0. So there must exist some set that in this great big union which actually contained x. If x ends up in the union, then some set, one of these sets that you were unioning, had to actually contain x. Now, because E alpha 0 is open, it implies that there exists an epsilon greater than 0 such that the ball centre of x of radius epsilon is completely contained within E alpha 0. The reason being that E alpha 0 is open, therefore every point must be an interior point. X is an element of E alpha 0, so there must exist some epsilon neighbourhood around the point x which is completely contained within this set E alpha 0. Okay, so find that, and now what we know is that this ball x of size epsilon, which is contained within E alpha 0. Well, E alpha 0 is contained within the union over alpha of E alpha. If this is contained within this, it's certainly contained within this because of the transitive property of containment. So this ball, therefore, has to be contained within this arbitrary union, E alpha. Okay, so that is why that is how you prove that countable unions also have to be open, because if you take any point that's in this great big arbitrary union, and I'm sorry if I said countable back there, in this arbitrary union, there must have existed some set which actually contributed that point. Now that set was open, therefore there must have existed an epsilon neighbourhood around that point x, which was completely contained within this set, and when you union this set up with loads of other sets, it's still going to be true that this epsilon neighbourhood is going to end up in the great big union, and therefore what I have found you is an epsilon neighbourhood which is a proper it's a subset at least of this union, and of course I should have said these should have all been potentially equal to, rather than proper containment, but I have found you a open ball around x of radius epsilon which is contained within this, which implies that x is interior, and since x was arbitrary, it implies that this union E alpha is also an element of the set of open sets, which was our big U. So what we have shown there is that if we take any metric space x and d, and we collect up the set of all open sets and call it big U, and then what we can then do is define a topological space, which is the set x along with the set U, and it will obey the axioms of topology. So what we have shown is that metrics give rise to topologies. Metrics give rise to topologies. The inverse is not true. It is not true that a topology necessarily has a metric which gives rise to it. Topologies that do have metrics that give rise to them are known as Hausdorff spaces, Hausdorff topological spaces. And there are easy examples. For instance, if you just let this topology be equal to the power set of x, then that is not a Hausdorff topological space. You can check that if you do that, it obeys all the axioms of topological spaces, because the empty set and the whole space are certainly elements. If you take any intersection, it certainly has to still be a subset of the space x, so it's still going to be in the power set. And if you take arbitrary unions, it's still going to be a set, but it does not have a metric that gives rise to it. Okay, so that's all for this video.